Okay, session is now being started. Is being recorded rather. And I'm going to pull up the PowerPoint. Okay, can everybody see the PowerPoint?
Yes.
Okay, very good. Hoy hablaremos del capítulo 23, óptica geométrica. Hablaremos de reflexiones y formación de imágenes en espejos esféricos y formación de imágenes con lentes convexas y cóncavas. Fool's Day.
Well done.
Oh, I amuse myself.
Well done.
I live for these moments. There's always a handful of students that would do just fine if I keep going on in Spanish. Gotta stick to English. Okay, so happy April Fool's Day anyway. It's a little challenging because there's a lot of material, chapters 23 and 24 to cover. So I thought what I would do is some of the trickier parts of both of these. It's a lot of material. I don't know if I'm going to be able to get through it. So let's just jump right into it. And Kelly, if something pops up that I should know, please read
I will. Yep.
Okay, light behaves like a ray, especially when interacting with things that are larger than its wavelength. And for visible light, wavelength is less than a micron, less than a millionth of a meter, something like that. Hundreds of nanometers, if you want. So what is a ray? Here I have the sun. Right, there's the sun, and light's coming out of the sun. So we have wave fronts because light is a wave, right? We're thinking about light as a wave. And the rays are lines that are perpendicular to the wave fronts. That's what rays are. So what are wave fronts? If it were, if you drop a stone in a pond, the wave fronts are where, these circles would represent where the level of the water is highest. And in between it would be lowest, and it'd be high and then low and high. For an electromagnetic wave, you could think of the amplitude of either the electric or the magnetic field being high, low, etc. But either way, the rays are just lines that are perpendicular to that. And if you're really, really far away from the source of the light, very far from the sun in this case, then the rays are essentially parallel, just because you're really far away from something like this. These rays, this bundle of rays here is actually this bundle here when you get really, really far away. You look carefully. So when we do the geometric optics, we really think about a bunch of parallel rays like this being the most useful rays. Okay, you know about reflection. This angle of incidence is equals the angle of reflection. Just be careful about how you measure these angles. The angles are always measured from the ray to a normal. A normal is simply a line that's perpendicular to the surface. You don't measure from the surface to the ray. That's a mistake that I see all the time. Okay, so light impinges on some kind of a regular surface, which is typically rough like this on some small spatial scale. And so the reflected rays go all over the place. So this is why if you have a perfectly dark room and you put a piece of paper on the table and then you put a flashlight on it, everybody in the room can see the spot of light on the paper. Because this kind of thing is going on, the light rays are being reflected all over the place. But if you're in a dark room and you put a mirror there and you put the flashlight on the mirror, you don't see the spot of light on the mirror unless your eye is in exactly the right place, right? At the right angle, according to the law of reflection. This eye over here doesn't see anything. Okay, so that's something important to keep in mind about reflections. And when this kind of thing goes on, different materials absorb different wavelengths. So if this were a red material, then the material would absorb most of the light that's not red and reflect the light that's red, and that's why things look red. You can stand in front of a mirror and you can see yourself on the other side. So how does that work? There are light rays that come out of you in all directions, but there's some special ones, like this one's from the very top of the head, reflects in the mirror and goes in the eye. This ray comes out of the end of the foot here, reflects on the mirror, and goes into the eye. And so the person infers that these light rays came from back here. You sort of extrapolate them back, right? The brain doesn't have a mirror built into it. You just assume that these light rays came from back there. And it looks like there's an image of you standing behind the mirror. Now, what about the rest of the image? Yeah, light rays from the rest of the person and the briefcase here, they go out in all directions and they fill in, they reflect off the mirror. Some of them go in the eye and they fill in the image. Okay, so this is a virtual image because it's called virtual because it's not a real image. It's made out of inferred light rays, not actual light rays. There's no actual light rays behind the mirror, in the wall behind the mirror. Right? All right, let's talk briefly about mirrors, forming image with mirrors. So what you do is you draw this axis, and here's the mirror. We're talking about spherical mirrors. So this mirror is a portion of a sphere whose center is C. Focus occurs halfway there. And I think you know that what the focus is. So let's just consider this object here, O for object, and figure out where its image would be. So there's ambient light, and light rays reflect off the object and go in all directions. But there's some special ones that we pay attention to. And we want to be able to follow them along to figure out where the image is. So light rays come out of the base of the object in all directions. There's a special one that goes right through these points, reflects right on the mirror there, and comes right back and keeps going. From that, we can conclude that the base of the image is somewhere on this axis. Okay, in order to figure out where the image is, let's now consider the top of the image. Light rays come out in all directions. There are a couple special rays that we pay attention to. So there's a special ray that comes out parallel to the axis, hits the mirror, and then therefore gets reflected through the focal point there. As one of the special rays. And so the top of the image is somewhere along this ray. Now we can consider this ray. It comes out of the top of the image, goes through the focal point first, and then hits the mirror and then gets reflected. Think about time going backwards. You have a ray that goes parallel to the axis, hits the mirror, and goes through the focal point. Right? And that's kind of like what we just did here, except now time is going forwards. It goes through the focal point first, hits the mirror, and then emerges back going parallel to the axis. Now we can put these together and see where they meet, because we know that the top of the image has to be somewhere along this ray. So they both meet there, and so that's where the image is. What we did is we said something about where the base would be. It would be on the axis. And then we located where the top is. And so all the rest of the light rays that come out of the object, some of them reflect off the mirror, fill in the space in between, and then fill in the rest of the image. And what does it mean to have an image? So if you put your eye where I'm indicating here, and you receive these light rays, these two light rays plus all the other ones, you see the top of the image. Because these light rays go into your eye and you see the top of the image. Now, if you put your eye over here, you receive the same light rays, and so you see the top of the mirror, the top of the image there. Okay, so I think you know that. You've seen that before, at least. The result then is a real inverted and smaller image, as you can see there. It's a real image because it's made out of real light rays. There really are light rays on this side of the mirror. So that's contrasted with the virtual image in the mirror, because these dotted lines are inferred. They're not real light rays, whereas these over here really are light rays, and so that's a real image. You can put a piece of paper there, and you'd see the image on the paper. Put a piece of paper in the wall behind a mirror, and nothing happens. All right, that was case one. I called it case one because I had the object farther away from the mirror than the center. Now, in case two, I'm going to put the object between the center and the focus. And the argument follows along the same way. You just get the same basic shape. It's just that you have a larger image. It's still real. It's still inverted. It's just larger. So when the object is right on the center, then you have an image that's the same size. And as you get closer, the object gets closer to the mirror, then the image gets bigger. So that's case 2. And case 3 is, excuse me, case 3 is going to be when the object is between the focal point and the mirror. This is a tricky one, so I want to go over this one. But the argument follows the same way. Is there a question?
Yes, she needs to leave and come back because for some reason Jolia couldn't see the everything. So she
Okay, go ahead and do that, and then you can come back. I did start the recording, didn't I? Yes, I did. All right.
Yeah.
All right. So the same argument. There's a light ray that comes out of the base and reflects and goes back. So we know that the base of the image is on the axis. Then you consider light rays that come out of the top in all directions. But there are some special ones. This is a special one. It emerges from the top of the object parallel to the axis, and therefore gets reflected through the focal point. Now here's another special one, which emerges from the top of the object as if it had come from the focal point, right, from that direction. But it goes away from the focal point, hits the mirror, and as a result, reflects and goes out parallel to the axis. Okay. So that's maybe one of the trickier ones. It's just a light ray that looks like it came from the focal point, and so when it reflects, it comes out parallel to the axis. So put these together, and now if you look at the mirror from the left, where I'm indicating here, if you put your eye here and you look to the right, you would receive this light ray and that light ray and all the ones in between, and you would infer that they came from over here. Just like when you look in a flat mirror, you infer they came from somewhere else. And so the image is over here, right, from the base to the tip, and all the other light rays fills in the image. The result is a virtual upright and a larger image. This is the case of the makeup mirror. You guys have makeup mirrors? For those who wear makeup. So here, this is just a regular mirror, and then there's one on the other side, and you get a magnified view of yourself. Well, this is how it works. Right? You put your eye here as the object, and you look, and what you see is your eye over here behind the mirror, but larger. Right? It's kind of basically impossible for me to show that to you. But when I put my eye up to it, this is the regular mirror, it's just me normally, and then I look at this one, I look bigger. I was playing around with this. I found this morning before lecture, I found out that the focal length is about 90 centimeters for this one. So the focal point from this mirror is about over here, that far. You guys have makeup mirrors?
Julia says, "Oh my God, connecting physics to day-to-day scenarios." I personally don't have one, but I'm sure a lot of people do.
What's the noise that I'm hearing? Is that somebody trying to speak?
It was me, but I have coffee being made in the background, so it's a little bit louder.
Oh, okay. Okay, so here are the 3 cases that I just discussed. And using this, I can tell you how I figured out the focal point of my makeup mirror. So if I'm really far away from the mirror, and I look in the mirror, and I see myself upside down and smaller. This is my face, and this is what I see. And then as I get closer, then I cross over the center. And then when I'm in between the center and the focal point, then I see myself still upside down, but bigger than I really am. And then as I get closer and closer and closer to the focal point, the image of me gets huge, it gets infinitely large, and still is upside down. And the moment I pass through the focal point, suddenly I'm right side up, but I'm still huge. And the closer I get to the mirror, I get a little bit smaller. So what I did is I looked in the mirror and I just moved back and forth until my eye got enormously large. And then I knew that I was near the focal point. So then I measured the distance I was away. All right. Convex mirror is just the same thing turned around. The mirroring is on the other side. The light comes from the left here. There's the object. Focal point you indicate on the right. There's the center. Again, it's a portion of a sphere whose center is here. Focal point is halfway between the mirror and the center. Okay, so to figure out where the image is that is formed by this convex mirror, same argument. Same argument for the base of the image must be on the axis. Light rays come out of the top of the object in all directions. Here's a special one that comes out of the object parallel to the axis, hits the mirror, and then gets reflected as if it had come from the focal point. Right, so you see I'm doing this dotted line to show that it's reflected as if it had come from the focal point. So that's one special ray. Here's another special ray. It's a light ray that comes out of the top as if and is aimed directly towards the center. When it hits the mirror, and the mirror is 90 degrees to it. So the angle of incidence is 90 degrees. It just reflects straight back. And then if you want, you can have this special ray. This special ray goes from the top of the object, hits the mirror at the axis, and then just reflects. So at this angle equals this angle, law of reflection. Okay, if you extrapolate that back, because remember, you're looking over here from the left at this mirror, you would extrapolate this light ray as if it had come from somewhere over there, and superimposing with all the other ones, you extrapolate them back, and the top of the image should be right here, and so the image is there. So this is a trickier one to draw. So it's just these three ones, and then you extrapolate backwards. The result is a virtual, upright, and smaller image. This is like the driver's side rear view, the passenger side rear view mirror. Objects may appear smaller than they really are in real life. Have you noticed that on the rear view mirror? It's useful because it enables you to see more of what's back there. Everything is smaller, so it's more on the mirror. Or sometimes you see, big convex mirrors up in the corners of stores or whatever, so that you can look up and see, around the corner or something like that. Okay. You've seen these equations, I know, right? The mirror equation.
Yes.
So the relationship between the focal distance, the image distance, the object distance, and also for magnification. So magnification is defined to be the image height divided by the object height. And it turns out that that's equal to negative image height divided by object height. Where does that come from? It comes from looking at the triangles and doing the geometry. It's tricky, so we don't do it. That's just what the equation is. I remember this because hi-ho equals minus dido. I don't know why. For some reason, that stuck in my head. But there are sign conventions. And so for mirrors, when any of these numbers, D0, D object, D image, or focal point are on the reflecting side of the mirror, they're positive. Right? So in this case, we have a concave mirror. The reflecting side is here. So this distance is the object distance measured from where the mirror hits the axis. There's the image distance, and there's the focal point. All these are positive numbers for mirrors. Whereas in this case, when we had the concave mirror, focal point was positive. The object distance is positive. The image distance is negative because it's on the other side of the mirror. By convention, this distance is considered negative. Negative by convention. For a convex mirror, the focal point is behind the mirror, and so that's considered to be negative. The focal length is negative by convention. And then for magnification, the object height is like this. It's always positive. The image height could be positive or negative. If it's negative, that means it's upside down. It's inverted relative to the object. And if the magnification is more than 1, then it's something that's bigger. If it's less than 1, then it's smaller. Okay. So there's a tricky homework problem that I got a number of questions on, so I thought I'd just do it. And mainly the trickiness is setting it up. So an object is placed a distance r in front of a wall, where r exactly equals the radius of curvature of a certain concave mirror. It's already a little bit tricky. At what distance from the wall should this mirror be placed so that a real image of the object is formed on the wall? Okay, so let's take it sentence by sentence. An object is placed a distance r in front of a wall. R exactly equals the radius of curvature of a concave mirror. So you have a picture that looks like this. Here is the wall. Here is the concave mirror. And then here's a line from which we'll measure distances. So r is the distance that the object is in front of the wall. And then the radius of curvature equals r. So we know that the radius of curvature is 2 times the focal length. Focal length is half of it. So the focal length is this, and that's the way I drew it. This is approximately half that distance. It's not exact, but I tried to draw it that way. It's kind of a little tricky to figure out. But this is basically the setup that we have. Because they tell you this distance, and they tell you that that's the radius of curvature. So the focal point has to be half of r. We have that. Interrupt me if you have questions. Okay, so with this setup, we have an image that's formed, followed the light rays like this, on the wall. It says that the image is put directly on the wall. And we would like to know what the distance is between the wall and the mirror, meaning this point of the mirror is this distance. Well, that image is that distance is the same as the image distance. So we would like to know what the image distance is. That would answer the question. At what distance from the wall should the mirror be placed so that the real image of the object is formed on the wall? I tell you it's a real image. Actually, since the real image, then we can infer that this is a concave mirror. Okay. So here is the object distance. And notice that there's a relationship between r, the object distance, and the image distance. So we can write the object distance as the image distance minus r. In other words, r plus object distance equals image distance, and then you can write this equation. Object distance is image distance minus r. Remember, what we would like to know is image distance, di. We can plug all these things into the lens equation. Right, so these are the 3 equations that we wrote down. We want, well, the 2 of them, and this one, and then we want to know what di is. So we can plug in for f, we can plug in for d0. And by the way, it does, since no numbers are given, what we want to do is we want to answer the question in terms of r. No, in terms of r. So we want to know what di is as a function of r. I think the statement of the problem says that. I just didn't type it. Okay, so we're going to take these equations and plug them into here. In the interest of time, I won't do it, but the steps are all here. You can go through them later. The result is a quadratic equation. So just say that again. These equations, these 2, plug them into lens equations, do some algebraic manipulations, and you'll get a quadratic equation for the image distance, like this, which then you can solve with the quadratic formula, and you get this. Now you're left wondering whether you should have a plus or a minus. Well, di we know is bigger than r just by looking at the diagram, so it has to be the plus sign. And so this is the final answer. Any question about this? The main thing is the setup. It's a tricky question because of this setup. In other words, just this part of it.
Dr. Barreto?
Go ahead.
When I worked out this problem, I did the plus and the minus sign, and I ended up getting 2 positive numbers, but you're saying we should choose the positive convention, like the adding convention, because of what?
Well, di is longer than dr. Di is bigger than r. So this should be a number that's bigger than 1.
Okay, that makes sense. Thank you.
Just the way it's set up. It's fine. Okay, so I think that's the trickiest problem on that assignment. There's Snell's law. I don't want to spend any time on this, just to remind you to measure the angle of incidence and the angle of refraction from the normal, from the line that's perpendicular to the interface drawn where the ray hits the other material. Draw the angles this way. Okay, so with refraction, then we have lenses, and we have converging lenses that do this. Already saw that, and diverging lenses which do this. Seen that? Let's go over some of the ray tracing cases. So first, the easy one to set it up. Here's a converging lens with these two focal points on either side. You can draw it that way. Here's an object. Follow the light rays. Okay, so the argument is, once again, the image of the base has to be somewhere on the base because a light ray comes out of the base, goes through the lens, and is not refracted. Then you consider light rays that come out of the top. They go in all directions, but there's a special one. This one comes out of the top parallel to the axis, gets refracted, and goes to the focal point on the other side. This special ray goes through the middle of the lens and is not refracted. Or I should say is refracted and then unrefracted. So the end result is the light ray just goes straight through. And then there's a special ray that comes out of the top of the object, goes through the focal point on the close side, gets refracted by the lens, and emerges parallel to the axis. Put them all together, and there's where the image is. And once again, the light rays that come from the whole rest of the object fill in the space between these lines and fill in the image. Okay? So you end up with a real inverted image in this situation. Here's the object distance. Here's the image distance. By convention, these are positive numbers. So unlike the case of the mirror, we now have light going through a lens. And by convention, image distances are positive if the image is on the other side of the lens. All right, so now a diverging lens. This is the tricky one. I showed you this in the lecture, but it was all drawn together and it's just a mess. So it's much easier to separate it out. So I had to make a lens like this with focal lengths that are pretty far away, and then put an object here. I had to do that so I could draw something intelligible. Okay, so once again, the image of the object's base is somewhere on the axis. We consider light rays that come out of the top. Here are some special ones. So one that goes parallel to the axis and then gets refracted as if it had come from that focal point. So there's this dotted line, and then it goes out that way. So the light ray goes this way and then out. There's one special ray. Another one is special. It just goes right through the middle and is not refracted, or is refracted and unrefracted. End result is the light ray just goes straight through. And then the other special one is one that comes out of the top of the object, directed towards the focal point on the other side of the lens. See the dotted line? But when it hits the lens, it gets refracted and emerges parallel to the axis. Right, so those are the three special rays. Superimpose them like this. And remember, for a lens, your eye is over here looking to the left. So you receive these light rays, and therefore your brain infers that they came from somewhere behind here. And notice that they all come together here. So here, this light ray is being extrapolated backwards along this dotted line. This one is being extrapolated backwards along that dotted line. And they all come together there. So that's where the image is. That's the image distance. And by convention, this is negative because the image is now not on the other side of the lens. It's on the close side of the lens. So this is a negative image distance by convention. Object distance is positive by convention because the object is on the side of the lens where the light comes from. End result is we have a virtual and upright image. Any question about these lines?
Dr. Barreto, I'm having trouble seeing where all of the three come together to form the image. Especially the middle one.
Is that better? You see my hand pointing?
Yes, I do.
Yeah, so if you extrapolate backwards, we drew these special rays already, right? This one, if you extrapolate backwards, is this dotted line. This one is just that ray. And then this one, extrapolated backwards, is this dotted line. And so just look to see where those two dotted lines and this dark one intersect right there.
Okay, I see now. Thank you.
So the image is a combination of a real light ray and two virtual light rays, if you will, extrapolated light rays. The end result is that it's a virtual image because not all of them are light rays. Again, if you put a piece of paper here, you won't actually make an image. You won't see it. I mean, the image would be there, but you won't be able to see it because it's a virtual image. Now, how do I unmagnify? There we go. There we go. Okay. All right, so same equations, and I already told you what the sign conventions are. The only strange thing is, so this is where I go to the sign conventions. The only strange thing is it's possible to have a negative object distance. And this comes about when you have combinations of lenses. So I'm going to describe a situation with two lenses, and the way you analyze it is one lens at a time. So here's lens A. There's an object. It forms an image over here. So we already did that. But suppose you put lens B there. So what happens when you next analyze it, the image of A, the image formed by lens A, becomes the object for lens B. And then you do your ray tracing, etc. But the way we set it up here, we put lens B on the left of where the image is. So this distance then is a negative object distance because it's on the right of the lens, and we're drawing things with the light coming from left. Right? There's the actual object, the original object, I should say, and then this is the image of lens A, and that becomes the object of lens B. Okay. So that's how you get a negative object distance. And there's a homework assignment, a homework problem on the assignment where you do this. And what you do is you just do them one lens at a time. You have to make a clear picture like this and lay out the distances because it gets a little complicated. So draw a clear and a very large picture, and you'll be able to work it out. All right, I've got maybe 15 minutes. Let's go on to chapter 24. There's lots in chapter 24. I just want to concentrate on the diffraction patterns, because I think that's the trickiest thing. And looking at the assignment for chapter 24, most of it is plug into the equations for these diffraction patterns. Okay, so chapter 23 is all about how light behaves like a ray. Chapter 24 is how light behaves like a wave. And the example is an experiment that was first done by Young. This is the double slit experiment. It has been described as one of the most beautiful experiments in science. So there was a poll done among scientists. What's the most beautiful experiment? And this one won. Was there a question?
No, Galia's still having problems seeing your content.
You can't see the screen?
I mean, I can. I'm not sure if anyone else cannot, but
I think it's just a problem on my end. So don't worry about it. I'm trying to figure it out, but I didn't know if anyone would have any ideas on how to fix it.
What I do is I close the browser and then open it again. I mean, just get out of Collaborate, but then shut down the browser and then open it again.
Okay.
At any rate, it's being recorded, so you'll have the recording available to you.
Okay, thank you.
All right, let's talk about Young's double slit experiment. We have light rays, or you could imagine water waves. In blue are the wave fronts. In red are the rays. And suppose you have a barrier that have two slits, two openings like this, S1 and S2. And you ask people, what are you going to see on a screen far away? A lot of people will assume that you'll see a bright spot here and a bright spot there, one for each one of the slits. If the openings are very large compared to the wavelength of the light, then that's what happens. You basically get two bright spots here and here. What's interesting is if the openings are not very large compared to the wavelength, the distance between these blue lines, then when the wave fronts emerge from the slits, they do this. They bend, as if you had dropped a stone of water, a stone into a pond of water, and you get the wave like this. And therefore, the two sets of wave fronts that come out of the slits interfere with one another, and you get a pattern on the other side of light, bright, dark, light, dark, light, dark. And you can do this with water waves, and you can do it with light. And so it's kind of amazing that it works with light. It's most clear if you use monochromatic light, so only one wavelength. That's easy to do with lasers, not so easy to do without lasers, but it's possible to do. Sort of filter out one color in particular. And you also need the wavefronts to emerge from the slits in sync, as it were. So you see that this wavefront hits the slit at the same time that one does. So here's the result of what you see if you use a laser with just two slits going through. I would demonstrate this if we were in person, because I have a laser and I have a little slide that's got two very closely spaced slits, and I can project this on the wall. If you use sunlight, then you can see something like this. It's blurry and you have a little rainbow effect because the diffraction depends on the wavelength. I highly recommend this YouTube video. There's no time for me to play it now, but very highly recommend it. It's entertaining. This is the Veritasium guy, I forget his name. He takes a big refrigerator box and diffraction pattern and goes out to a beach and just asks random people, what's going to happen if I put sunlight through these two things, and then you can look in the box where it's dark. What are you going to see? And it's kind of amusing, and then he's got a nice way of explaining it. So please go and watch this video. It's highly recommended. We've seen this kind of thing before with sound. Right? We had two sound speakers that were in phase, and they put out sound. And so there were regions where there was loud and soft and loud and soft. I told the anecdote about me trying to study in the library, and there were two buzzing light fixtures above. And I had to move left and right until I could find where the interference caused the sound to go away, and I could actually concentrate on my work. So at a point like C, you've got waves that arrive at C in phase. At C, so here we've got one wavelength, two wavelengths, three wavelengths, and a half, or a quarter. And then here we've got one wavelength, two wavelengths, three wavelengths, and a quarter. So at C, the waves arrive in sync. And so there's a constructive interference going on. In contrast, at a point D over here, we have one wavelength, two wavelengths, and 3/4 coming from speaker A, or light source A. And B, we've got one wavelength, two wavelengths, three wavelengths, and 1/4. So at point D, there's a peak from one and a trough from the other. And so we have destructive interference, and there's no signal there. Same thing happens with the light through the two slits. Here are the two slits. Here's the screen. So L is a large distance. And the light impinges on here. If you measure the distance from this slit to this point, directly opposite the middle point of the two slits, and you measure the distance from there, it's the same. So the wave travels the same distance, and so we have the same number of wavelengths exactly. And when the light arrives there, there's constructive interference. Again, I'm assuming that the waves that go through the slits are synchronized to begin with. See how this peak is here, and that peak is there, and that peak is there, and that peak is there. So then if they go the same distance, they'll arrive at this point and constructively interfere. But if you look a little bit higher on the screen, notice that the wave that comes from the top slit travels a certain distance. The wave that travels from the lower slit travels a little bit more distance. And here's that extra distance. Right? So here's a line that's perpendicular to this line. So you see that that distance equals this distance. This is the little extra piece. If that extra piece were equal to 1/2 of a wavelength, then when those waves get to that point on the screen, they're out of phase by half a wavelength, and so we have destructive interference. A peak arrives when a trough arrives from the other. They destructively interfere, and so you have dark, no signal there. Right? Keep increasing the angle, and we get to a point up here where the extra distance equals an entire wavelength. Then, at that point, you still have two peaks. You have two peaks arriving at the same time, right? Because once this wave has traveled that extra distance, from then on they're in sync again, and they arrive there at the same time. And so we have bright again. So, as a function of the angle, you'll end up with bright, dark, etc. And the same thing with the angle going the other way. So that's why we get these interference patterns that look like that. There's bright. Remember, so if you look at the screen, your eyes are where the slits are, and the angle is measured outward this way. Bright, dark, bright, dark, bright, dark. And it gets darker because the light is traveling farther, and the intensity gets dispersed a little more. Okay. So to quantify that, you can draw this picture where we have the ray instead of the wave, right? And you can look at this triangle here, and there's the extra distance. I'm indicating here, indicated by this little bracket. That's the extra distance traveled by the wave that comes out of slit 2, compared to the distance traveled by the wave that comes out of S1. Well, that triangle, look at this angle. This angle is the same as that angle. So we have a right triangle, and this side of the triangle is equal to hypotenuse sine of theta. So that extra distance can be expressed in terms of the angle and the distance between the slits. Set that equal to an integer number of wavelengths. Here, m is an integer. And that means that at that angle, you'll have constructive interference, and so you'll get a bright spot. So this equation identifies where the bright spots are, where m is an integer. That can be 0. So 0, 1, 2, 3, 4, etc. So you get a pattern that looks like that. And here's a graph of the intensity of the light versus the distance along the screen. And so here's the middle part. That would correspond to n equals 0, where this extra distance is nothing. If m is 1, then you get this bright spot or that's bright. Either you can measure the angle either way. That corresponds to this extra distance being 1 wavelength, and so you get constructive interference, etc. All right, so I hope that's clear. Let's do an example in the remaining minutes. Okay, so light of wavelength 720 nanometers falls on 2 slits and produces an interference pattern in which the 4th order fringe is 50 millimeters from the central fringe, so fringe meaning bright spot, on a screen which is 1.5 meters away. So with this information, they ask you to figure out the separation between the 2 slits. So here is the picture. The secret, by the way, of physics is to draw a good picture. And drawing a good picture is a skill that you can develop. It's not something that you're born with. Anyway, here is a good picture for this problem. Here are the 2 slits. Here is the screen. Screen is a distance capital L away. That's the 1.5 meters. We don't know what this distance is. We want to figure that out. And then here is the bright, dark pattern. It's depicted by this sort of wavy line, kind of like a histogram, if you will, where this means that this spot here on the wall is bright. Right? This wiggly thing doesn't actually exist. It's just indicating that this spot here on the wall is bright. This is dark. This is bright. This is dark. This is bright. This is dark. So don't get confused by that line. It's not really there. It's just indicating bright, dark on the wall. Okay, so this is the central fringe, m equals 0. The next bright spot is here, so m equals 1, 2, 3, and 4. So when it refers to the 4th order fringe, we're talking about this bright spot here. Right, so 1, 2, 3, 4. All right, so there's the setup. And the 4th fringe, by the way, is a distance h away from the central fringe. So that's not given, that is given the problem, because it says that the fourth order fringe is 50 millimeters from the central fringe. So H is 50 millimeters. All right, here is the equation for two-slit diffraction. We want to solve for D. Here it is. What do we know? Well, the M is going to be 4 because we're talking about the fourth order fringe. Lambda is given, 720 nanometers. Sine of theta, we don't have the angle theta. But what we do have is this big right triangle. One side of it is 50 millimeters, and the other side of it is 1.5 meters. So clearly not drawn to scale, right? But is drawn in such a way that you understand that we have a right triangle here. So the tangent of the angle is H over L. Plug in the 50 millimeters for H and the 1.5 meters for L. It converts so that the units are consistent, and we can solve for the angle, and it's a little bit less than 2 degrees, 1.9 degrees. Now that we have that angle, we can plug it into that formula to get the slit separation. There it is, plug in the numbers, and your answer is 0.086 millimeters. So these two slits are really, really, really close together. Okay, most of these types of problems involve a question like this, and involve, excuse me, a geometry like this, and involve a big right triangle of this sort. So you should draw out a problem like that and understand this sort of spatial geometry of how the experiment is done.
Dr. Brito,
Okay. Yeah.
how did you know it was constructive interference? Did it tell us that in the problem to use that?
Well, it says the fourth order fringe. So fringe means bright spot. So there's constructive interference to create a bright spot.
Okay, thank you.
Bright spot here, bright spot there, bright spot there, bright spot there, bright spot there. Yeah, fringe is a funny name. I guess because it's fuzzy. If it's really monochromatic light and everything is nice and clean, you just get lines. Okay, you can make a diffraction grating, which is just a whole bunch of slits, and the argument is exactly the same, and you get exactly the same equation. Instead of sort of a blurry blob, you get very distinct lines. It's just because the constructive and destructive interference is more complete and more angularly defined. But in the last minute, I'm going to point out that you can have diffraction with a single slit. So a single slit will create a diffraction pattern, which is a little bit different. It's one big bright spot where you would expect it to be, and then really much attenuated other bright spots farther away. But they can be understood this way. So imagine that you have just a whole bunch of rays going through the open single slot. That'll create a bright spot on the screen. But then at an angle theta, you have this situation here. In this case, the extra distance, traveled by this ray relative to the one on the other extreme is one wavelength. And so that light ray will interfere with the one in the middle, which has an extra distance of just half a wavelength. So when they get to the screen, this light ray, I'm indicating here, and that light ray will destructively interfere. Similarly, this second light ray will destructively interfere with that one, and this one with that one, and that one with that one. So they'll all go away. So you get a dark fringe on this when this extra distance here is one wavelength. That's different from the situation before. At a little bit larger angle, where this maximal extra distance is 3/2 of a wavelength, then you get a bright spot again. And the reason why is because 2/3 of these rays cancel each other, and you have 1/3 left over. Right, so for these top 2/3, you have the same argument as I had in the middle here, and then you have these other ones left over. So you get a pattern that looks like this: very strong bright spot in the middle, and then weaker bright spots farther out. The equation follows by setting this extra distance for a dark spot equal to a wavelength. So you get the same equation, except that it gives you the dark spots. Here, capital D is the width of the opening of the single slit. So it looks like the same equation, but it's interpreted differently. The D is not the separation between two slits because there's only one slit. And it tells you where you have dark spots, not bright spots. I'm out of time, and I forgot to take screenshots. I'm going to take quick screenshots, and then I know everybody has to leave because you have other things to do. I hope this was helpful. I know I tried to fit in maybe too much stuff. But if you have questions, feel free to email me. I have an office hour coming up tomorrow. If you tell me in advance, I'll try to address them, and they'll be included. I have the screenshots. All right. Have a good day, everybody.
Have a great day.
Again, I hope it was helpful.
Always.
Let me know if it's helpful. If it's not helpful, I want to change things so that it is helpful.
No, for me at least, it's very helpful.
Good, I'm glad. Yeah, sign conventions can get kind of tricky. Okay, see you, everybody. That's a fun April Fool's joke. I crack myself up anyway. Okay, I'm going to stop the recording now. All right, have a good day. Have a good day, everybody.